When I was first learning about propositional logic, which is what we're technically looking at right now, this is one of the things I found confusing. What was the difference between the biconditional being used between P and Q and saying that P is equivalent to Q? Let's look at a couple of examples to make that more clear, what the distinction is. Let's remind ourselves that the biconditional here is really a shortcut for writing this. P implies Q and Q implies P. Okay? And here, these could be atomic statements, like it could be, P is equal to pigs fly, which has a truth value. It's either true or it's false. Or they could be compound statements like this. Q is equal to, pigs fly and cows sing. It could be either one. Now let's just do a simple one with some atomic statements since it'd be easier to create the truth table for the first one. So let's have our A and B here. So true, 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 false, false, true, false, false. And so now let's create this. A implies B. So this would be true. This would be false. This would be true. This would be true. Remember, the only one's false is where A is true, or the left thing, and the right thing is false, like we have here. B implies A. Now we're going true and true is true. False and true is true. True and false is false. And false is considered true. Okay? So note that these are different. Okay? And so now when I write this, A implies B and B implies A, which is really just writing the biconditional here between A and B. This is just the equivalent of this. True and true is true. False and true is false. True and false is false. And true is true. Okay? Can I always write the biconditional between two well-formed formulas? Yes, it's a logical connective. So I'm not making any claims. When I write P if and only if Q, which is what this is, I'm not making claims about it always being true or always being false, or like in this case, a mixture of the two. I'm just connecting two things together. Okay? Now let's do a slightly different one. Let's look at this. In fact, let me go to a different sheet of paper. A implies B, and not B implies not A. All right. So once again, create my table. True, 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 false, false, true, false, false. A implies B, true, false, true, true. Let's produce not B and not A to make it easier to write this. Of course, if you're doing these yourself, you don't necessarily need to rewrite the values, but for me, it reduces my opportunity for mistakes. So not B will be false, true, true. Not A will be false, false, true, true. And so now where's the one that would be false? Would be this right here. True and false. So true implies false is a false statement. The rest are trues. And so now when we write this, A implies B implies B implies, or not B implies not A. So we're looking at this and this. So true and true is true, false and false is true, true and true is true, and true. And we do it the other direction, because I'm working out the biconditional here. Sorry, this should be A. So true and true is true. False implies false is true, true, and true. And now I'm going to do the biconditional. Let's call this, for the sake of ease, we'll call this whole thing C and D. So when I write C, if and only D, remember this right here is really this and this. Well, these are all true, these are all true. So it's supposed to be true, 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 true. Okay? So what happened here? Well, now we have a tautology for this expression. So this right here, remember this right here will be this implies this, that's this, and this implies this, which is this, which I've written as C and D to make it easier, but it's all true. So we could write here that A implies B is equivalent to not B implies not A. So everywhere I use this, I could use this and get the same exact result. So this is not a logical connective. What this really means is that A implies B, if and only if not B implies not A, is a tautology, which we saw here. We go back to the original example. For this particular example, okay, this was not a tautology. So once again, the biconditional is logical connective. I can always write that between two well-formed formulas. But that doesn't guarantee that the values will be all true or all false or a mixture of those. When it happens to be all true, then we have a tautology, and we can then write it as an equivalence. Because once again, back here, if I were to try to replace A implies B with B implies A, well, when we got to say right here, we see we get two different answers. So they're not equivalent. And also when we look at here, we get two different answers. So they're not equivalent. So I would never want to take this and just call it this. But there's times when having this, it might be preferential to write this or vice versa, because they're equivalent. Just like if I have 3 plus 4. Wherever place in a mathematical expression I have this, I could just write 7, right? It'd be equivalent. But if there were some times when it didn't work out to be 7, well, then they wouldn't be equivalent. So that's the distinction, or that answer my question. What's the difference between this and this? This is a biconditional with the additional requirement that it's always true.